your video lesson from me on 3.4 velocity and rates of change. There are some things that I'm going to skip through that I'm not necessarily going to be talking about or writing down the answers as in depth as what they might be in your notes. So please do refer to the PDF and the notes for some of the things that I skip over. And of course, you guys also have the book video, which goes through everything in a lot more detail than what I'm going to cover. So this is really going to talk about velocity and the relationship between the first derivative, the second derivative, and your rates of change. So this is something we've already kind of been talking about. Your instantaneous rate of change is f prime at a. This is using the limit definition, and again, the limit has to exist at a for this to even happen. We are still going to be using the shortcuts, though. We're not going to be using the limit definition here, but this is the official instantaneous rate of change definition. Okay, so for example 1, this has a couple different parts here, and I will scroll. I know my little video thing is in the way for part of this. So find the rate of change of the area A of a circle with respect to its radius r. So the first thing you need to think about is, what is the formula for area of a circle? Well, area of a circle is pi r squared. So if we are finding the rate of change of that with respect to the radius, that would be dA dr. That means r is like your x variable, a would be like your y variable. Remember, this pi out in front is a constant, so it would be the same thing as if I had, say, a 3x squared, and I was finding the derivative of that. We can use the power rule, so I bring the 2 down and multiply it by the pi, and then I subtract 1 from the exponent of r. So that'd be r to the first power. So the derivative is 2 pi r, which should look familiar to you. I think I might have alluded to this earlier in class. That's actually the circumference formula. So interestingly enough, the rate of change of your area is circumference when you're talking about a circle. And part B, evaluate the rate of change of A at r equals 5 and at r equals 10. So if we are evaluating your dA dr at r equals 5, that means you are plugging in a 5 for the r. So when we plug in the 5, I get 10 pi. When we plug in the 10, that's 2 pi times 10, which is going to be 20 pi. So 10 pi and 20 pi are going to be my rates of change there. And then finally, if r is measured in inches and a is measured in square inches, what would be appropriate units for dA dr? So a would be your inches squared. So that's inches squared. R is in inches, so this would be inches squared per inch. This would not be appropriate to reduce because you actually have inches squared per inch as a fraction. It would not be appropriate to reduce that to just be inches because you do have to have something per something because it is a rate. This dA dr is a rate of change, so inches squared per inch would be the proper way to express the measurement. So the rate of change at 5 is going to be 10 pi inches squared per inch, and at 10 is going to be 20 pi inches squared per inch. So here's a couple other important things to know about this. S is going to be your function for f. That's your object moving along your s-axis at time t. S we do use as position. They don't use P because P typically stands for something else in calculus. So S, when you see that S, that stands for position. Your displacement, and I've had so many students mess this up. Your displacement of your object over your whatever your time interval is if you're going from T to delta T, it's wherever you're at when you end minus where you started at the beginning. A lot of students forget this part. They just think that displacement is just where you end up. But if you start at 5 and you end at 10, your displacement is 5. your displacement isn't 10, it would only be 10 if you were starting at 0. So you do need to make sure that you're careful that you are subtracting out wherever you're starting at if you need to find displacement. And displacement is one of the very common things that they're going to ask us to find in calculus. And then we have average velocity. This again is just the slope formula. It's your displacement over your travel time. So whatever your change in S is over your change in T. And you can see here's your displacement, and then you would divide by whatever your total change of T is. Scroll here so you can see this. If you want to find the velocity, your exact instant, you would take that limit as this delta T is going to approach 0. So as your change in time is going to approach 0. We are going to be using, again, the shortcut. We're not going to be using the limit, but these are important things to note about velocity as far as position goes. Velocity is the derivative of position, which is what we have here. Your instantaneous velocity is going to be your derivative of your position function s, and it's with respect to time. So you can see here that's ds dt, which is the same thing as the limit as delta t is approaching 0 of the other equation that we had. So this is something that you, we're not going to be using the limit definition. We are going to be using those shortcuts since we already went over those in 3.3. So don't worry about having to use the limit thing. But the limit is very important for the actual proof that goes along with this definition. Example 2 is something I would like you guys to read in the textbook. I actually don't have anything on that on my notes right here, so please read over that. I believe it does go along with like velocity and position and all those kinds of things being related. Okay, next. Velocity is going to tell us direction. So if you take your derivative and your velocity is, say, negative, that means your object is moving in the negative direction. If it's positive, it's going to be moving in the positive direction. But there are times when it doesn't matter what direction we're going. It just matters what the value is. And that's where speed comes in. Speed is going to be the absolute value of velocity. So you're just going to take whatever you have and turn your sign positive. So if your velocity was negative 100, the speed would be 100. You just have to make that positive. Doesn't matter what the original sign was. So this brings us to example 3. And this is one because there's a lot that goes along with this. I am going to talk through this. This is in your textbook. So this is something where you can go through and you can look at how the book talks about these and how they would write this up in order to figure out what you should be having here. And I am going to scroll just a little bit because I see my camera here is in the way. Well, let's read through the first part here. So you have a student walking in front of, and I actually might have the answer down here below. A student walks around in front of a motion detector that records her velocity at 1-second intervals for 36 seconds. So we could actually go the whole way up to 36 seconds on our graph. She stores the data in her graphing calculator and uses it to generate the time velocity graph shown here. Describe her motion as a function of time by reading the velocity graph. When is her speed at a maximum? So, and I'm going to it makes more sense to be moving from left to right here. So you can see here, when she starts out, she's at 0, which means she's not moving. Her velocity stays the same. She is going to be moving in a positive velocity, and notice it's not a consistent velocity. She's actually going to be speeding up. So she's going to be moving, she's speeding up, and then she's moving at this consistent 10 velocity, and then she's still moving towards the right, but she's going to be slowing down and going slower. When she hits 12, that's where she starts moving in an opposite direction. So she's going to be going back then. And then she's going to be reaching her breaking point here. You can see the bottom of the graph, where she's still moving towards that left-hand direction, but then eventually she's going to be slowing down, and then she's going to be stopping for a period of time. So it looks like from about 22 to 28, she is stopping, and then she's going to be turning and moving in the positive direction again. So remember, velocity, anything that is above the axis would be where she's moving right. Anything that's below is where she is moving left. And I'm sorry, my M looks a little bit weird there. Let's just take a little bit of that away. So anything above the axis, she's moving to the right. Anything below the axis, she's moving to the left. This part here is where she is not moving at all because her velocity is 0 there. And I believe, if I'm correct here, you can see here, I actually have this already typed up. So here would be how you would describe what's going on. She is going forward with an increasing velocity, and then she's going to move forward at a constant velocity, and then she's going to start slowing down while she's still moving forward. When she hits to 12, she's going to move backward until she gets to 22, and then afterwards she stays still for about 6 seconds, and then she's going to move forward again. Her speed is a maximum at about 18. So speed, remember, it's the highest positive or negative value. The highest she goes in the positives is 10. The lowest she goes in the negatives is almost down to negative 12. So at that time equals 18, that would be where her speed is a maximum. And again, this is one that I would really suggest reading through in the book. And I'm sure that the video that goes along with the book also does a really great job of explaining how this question would be solved. So this is just our first velocity graph that we've really considered with direction moving. I know we've talked about positive and negative slopes, but now we're actually going to be thinking about movement. Typically, unless they tell you otherwise, your movement, you're thinking about moving to the right is a positive velocity, moving to the left is negative. Although if you're on the y-axis, moving up would be positive, moving down would be negative. And it can go both ways there. And I see my calibration is going all kinds of haywire. So let's do this. No video would be complete without something going wrong in the middle of it. Okay, so let's try that again. We are going to go forward. Okay, so now we're to acceleration. Acceleration is the derivative of velocity, and again with respect to time. So you have position. The derivative of position is velocity. The derivative of velocity is acceleration. You can see acceleration then is the second derivative here. That is the second derivative of position. Couple of important things to point out here. For free-falling objects, this S equals 1/2 g times t squared. That is used for free-falling objects on Earth, where g is going to be your g is your acceleration due to gravity. Let me scroll here if it'll let me. I might need to go to a different video so we can get a handle on this a little bit. The English system, your g is going to be 32 feet per second squared. That is what we use in this class quite a bit. And then the equation you would see is 16t squared. Whereas in metric, you're looking at 9.8, and so that equation is going to be 4.9t squared. So that's a little bit of difference between the English and the metric system. Okay, and this brings us to example 4. I think this is a good place to stop this video and make sure I have all my technical difficulties figured out. So before you go on to the second part, there is an additional handout for the PDFs that goes through example 4. It is also in your textbook, and I do have the entire question worked out on the PDFs for your notes, so you can bring that up and follow along. I am going to be referencing the worksheet while I'm going through this, as well as the notes, just to answer the questions and to go through and solve them. So please go back and rewatch anything in this video that you're not sure of. We have a few more examples that are going to allow us to finish this out. And just like with everything else that we do, please contact me if you have any questions.